Budani, Assistant Professor at LJ Institute of Engineering and Technology. Today in Sequence and Series, I will teach you new topic, that is root test, alternating series test. So let's start. First of all, we will see the statement of Cauchy's root test. If sigma n is from 1 to infinite, un is a series with positive terms, and if limit n tends to infinite, un raised to 1 upon n is equals to L, then first condition, for L less than 1, series converges. Second condition, for L greater than 1, series diverges. Third condition, for L equals to 1, the test fails. Now you have to note down this important point. If un is of the form Vn raised to n, then the root test can be used. Now we will see examples related to Cauchy's root test. Example number 1. Test the convergence of the series sigma n is from 2 to infinite 1 upon log n raised to n. So here is the solution. Here un equals to 1 upon log n the whole raised to n. Now if we will find out un raised to 1 upon n, so we will be having 1 upon log n, because 1 raised to 1 upon n, that is 1, and log n the whole raised to n, it's 1 upon n power, it will become log n. Therefore, limit n tends to infinite, un raised to 1 upon n, that is equals to limit n tends to infinite 1 upon log n. Now as n tends to infinite, log n it tends to infinite because the value of log infinite is infinite, and 1 upon infinite it tends to 0. So this is equals to 1 upon log infinite, and as log infinite is infinite, this is equals to 1 upon infinite, and 1 upon infinite is 0, and 0 is less than 1. So by root test, series sigma un is convergent. Now this is second example. Is the series sigma n is from 1 to infinite n e raised to n convergent? So here is the solution. Here un equals to n e raised to n. So we have un raised to 1 upon n, that is equals to n e raised to n the whole raised to 1 upon n. Therefore, limit n tends to infinite un the whole raised to 1 upon n, that is equals to limit n tends to infinite n e raised to n the whole raised to 1 upon n. So this is equals to, if you will simplify e raised to n the whole raised to 1 upon n, so it will become e multiplied by limit n tends to infinite n raised to 1 upon n. Now this e will be as it is, and we have limit n tends to infinite n raised to 1 upon n, that is equals to 1. So this limit equals to 1. Now if you will multiply e by 1, so the result is e, and the value of e is 2.718281, which is greater than 1. So by root test, series sigma un is divergent. Now this is example number 3. Test the convergence of the series 1 cube upon 3 plus 2 cube upon 3 square plus 3 cube upon 3 raised to 3 plus 4 cube upon 3 raised to 4, and so on. So here is the solution. Here un equals to n cube upon 3 raised to n. As you can see, this is 1 raised to 3, 2 raised to 3, 3 raised to 3, 4 raised to 3, and so on. So in general, this nth term will be n cube, and for the denominator sequence 3 raised to 1, 3 raised to 2, 3 raised to 3, 3 raised to 4, its nth term will be 3 raised to n. Now we will find out un raised to 1 upon n, that is equals to n cube upon 3 raised to n the whole raised to 1 upon n. Therefore limit n tends to infinite un the whole raised to 1 upon n, that is equals to limit n tends to infinite n cube upon 3 raised to n the whole raised to 1 upon n. So this is equals to limit n tends to infinite n cube the whole raised to 1 upon n, it will become n raised to 3 upon n, and upon 3 raised to n the whole raised to 1 upon n, it will become 3. Now this is equals to limit n tends to infinite, writing 3 raised to 3 upon n as n raised to 1 upon n the whole raised to 3 divided by 3. Now the limit n tends to infinite n raised to 1 upon n, its value is 1. So it will become 1 cube, which is 1, and divided by 3. So answer of this limit is 1 upon 3, and 1 upon 3 is less than 1. So by root test, series sigma un is convergent. Now we will see what is an alternating series. An infinite series with alternate positive and negative terms is called an alternating series. So this is the example: 1 minus 1 upon 2 square plus 1 upon 3 square minus 1 upon 4 square plus 1 upon 5 square minus 1 upon 6 square plus dash dash dash, and this is equals to sigma n is from 1 to infinite minus 1 raised to n minus 1 into 1 upon n square. Here you can see that first term is positive, then after second term is negative, third term is positive, fourth term is negative, and so on. So this is the series called alternating series. Now we will see Leibniz test for alternating series. If the alternating series sigma n is from 1 to infinite minus 1 raised to n minus 1 un, that is equals to u1 minus u2 plus u3 minus u4 plus u5 minus u6 and so on, satisfies the following conditions. Condition number 1, that is mod un is greater than mod un plus 1 for all n. Condition number 2, limit n tends to infinite mod un equals to 0, then the series is convergent. So this is the Leibniz test for alternating series. Now we have this example related to Leibniz test. Test the convergence of the series sigma n is from 1 to infinite minus 1 raised to n plus 1 upon log n plus 1. So here is the solution. Here the given series is alternating series. Whenever you will find the terms like this, that is minus 1 raised to n or minus 1 raised to n minus 1 or minus 1 raised to n plus 1, then that particular series is an alternating series. Let mod un, that is equals to 1 upon log n plus 1. So it will be a series of positive terms only. So for that purpose we are neglecting this term, that is minus 1 raised to n plus 1. Now we will find out mod un minus mod un plus 1, and this is equals to 1 upon log n plus 1 minus, for un plus 1 we will replace n by n plus 1, so it will become 1 upon log n plus 2. Now taking LCM, log n plus 1, log n plus 2, multiplying this one by log n plus 2, then after this minus sign, multiplying this one by log n plus 1. Now this is always positive for n greater than or equals to 1. Therefore mod un is greater than mod un plus 1, as mod un minus mod un plus 1 is greater than 0. Now we will see condition number 2, limit n tends to infinite mod un, that is equals to limit n tends to infinite, and mod un is 1 over log n plus 1. Now as n tends to infinite, logarithm of infinite plus 1 tends to logarithm of infinite, and the value of logarithm of infinite is infinite. So this is equals to 1 upon infinite, and 1 upon infinite is 0. Therefore both the conditions are satisfied. Therefore the series is convergent by Leibniz test. Now we have this second example. Test the convergence of the series 1 minus 1 upon 2 root 2 plus 1 upon 3 root 3 minus 1 upon 4 root 4 plus dash dash dash. So here is the solution. Here the given series is an alternating series. As you can see, we have alternate positive and negative terms. So this series, that is equals to sigma n is from 1 to infinite minus 1 is to n minus 1 into 1 over 1 is fixed in the numerator, and in the denominator we have sequence 1 root 1, then after 2 root 2, 3 root 3, 4 root 4 and so on. For the sequence 1, 2, 3, 4 and so on, its nth term is n, and for the sequence root 1, root 2, root 3, root 4, its nth term will be root n, and this minus 1 is to n minus 1 is for alternate sign. Now first of all we will find out mod un. So mod un, that is equals to, neglecting this term, that is minus 1 is to n minus 1. So this is equals to 1 upon n root n. Now we will find out mod un plus 1. So for un plus 1 we will just replace n by n plus 1. So this is equals to 1 upon replacing n by n plus 1 and again replacing n by n plus 1. So it is root n plus 1. Now mod un minus mod un plus 1, this is equals to, this is mod un 1 upon n root n minus this is mod un plus 1, that is 1 upon n plus 1 root n plus 1, and this is positive for all n greater than or equals to 1. So we have mod un minus mod un plus 1, that is greater than 0. Therefore mod un is greater than mod un plus 1. So condition number 1 is satisfied. Now we will see condition number 2, that is limit n tends to infinite mod un, and this is equals to limit n tends to infinite mod un is 1 upon n root n. As n tends to infinite, 1 upon infinite tends to 0. So second condition is also satisfied. Hence by Leibniz test the given series is convergent. So in today's lecture we have discussed root test and Leibniz test and examples related to these topics. Thank you for watching this video. I will see you in the next lecture.